Section 1. The prevailing paradigm, a materialistic view of memory. The human brain is an incredibly complex organ, capable of astonishing feats. We use it to think, to feel, to learn, and to remember. Given its central role in our lives, it's no surprise that we often think of the brain as the seat of our memories. This idea, that memories are physically stored within the brain, has been the dominant paradigm in neuroscience for decades. This perspective aligns with a materialistic view of the world, a philosophy that reduces all phenomena to physical processes. In this view, our thoughts, feelings, and memories are nothing more than the product of neurons firing and synapses connecting. However, emerging evidence suggests that this picture might be incomplete. Could our memories be something more than just electrical and chemical signals in the brain? Could there be another, perhaps even more profound explanation for how we store and retrieve our past experiences? These are the questions we will explore in this essay. Section 2. Challenging the orthodoxy, the case against brain-based memory. The notion that memories are not stored in the brain may seem counterintuitive at first. After all, we know that damage to the brain can result in memory loss. However, a growing number of scientists and researchers are beginning to question the traditional view of memory storage. They argue that the brain, while undoubtedly involved in memory processes, may not be the actual storage site of our memories. This alternative perspective suggests that memories might reside elsewhere, perhaps in a realm beyond our current scientific understanding. This shift in thinking challenges the foundations of traditional neuroscience and opens up exciting new avenues for exploring the true nature of memory. In the following sections, we will delve into the evidence that supports this radical departure from conventional thinking. We will examine compelling cases, scientific studies, and the insights of leading experts who are challenging the orthodoxy and pushing the boundaries of our understanding of memory. Prepare to have your assumptions challenged and your understanding of the human mind expanded. Section 1. HSAM. A glimpse into extraordinary memory. Imagine possessing a memory so sharp that you can recall specific events from almost any day of your life in vivid detail. This is the reality for individuals with highly superior autobiographical memory, HSAM, a rare condition that challenges our fundamental understanding of memory storage. People with HSAM exhibit an uncanny ability to remember personal experiences with remarkable accuracy and detail. They can effortlessly recall events from decades ago, often with a clarity that most people can only dream of. This remarkable capacity for memory retention raises profound questions about the limits of human memory and the nature of memory storage itself. Studies on HSAM individuals have revealed fascinating insights into their exceptional abilities. These individuals do not employ mnemonic devices or special memory techniques. Instead, their superior memory seems to be an inherent trait, an effortless ability to record and access their past experiences with remarkable fidelity. The existence of HSAM challenges the prevailing notion that memory is a limited and fallible faculty. It suggests that the human mind may be capable of far greater feats of memory than we ever thought possible. The implications of HSAM extend beyond the realm of neuroscience, prompting us to reconsider our understanding of human potential and the nature of consciousness itself. Section 2. The puzzle of HSAM. Challenging neurological explanations. The extraordinary memory capabilities of HSAM individuals have captivated scientists and researchers alike. Numerous studies have been conducted to unravel the neurological underpinnings of this condition, hoping to find a correlation between brain structure or function and HSAM. Surprisingly, these studies have consistently failed to identify any significant neurological differences between HSAM individuals and those with ordinary memory. Brain imaging studies have shown that the brains of HSAM individuals are structurally similar to those of control subjects. This lack of a clear neurological explanation for HSAM throws a wrench into the traditional view of memory as solely a product of brain activity. If memories are simply stored in synapses, as the prevailing theory suggests, then one would expect to find significant differences in the brains of individuals with vastly superior memory capabilities. The fact that HSAM individuals exhibit such extraordinary memory abilities without any corresponding neurological anomalies suggests that our understanding of memory is far from complete. It raises the possibility that factors beyond the physical structure of the brain may play a crucial role in memory storage and retrieval. Section 3. Beyond the physical questioning, the synaptic theory. The synaptic theory, which posits that memories are stored in the connections between neurons, has been the dominant model in neuroscience for decades. However, the existence of HSAM and other memory phenomena, coupled with recent scientific findings, has cast doubt on the completeness of this theory. One of the main challenges to the synaptic theory comes from the dynamic nature of synapses themselves. Synapses are constantly forming, breaking, and changing strength in response to experience. This process, known as synaptic plasticity, is essential for learning and memory formation. However, the dynamic nature of synapses also presents a problem for the idea of long-term memory storage. If memories are stored in synapses and synapses are constantly changing, how can memories persist over time? The proteins that make up synapses have a relatively short lifespan, typically turning over within weeks or months. If memories were solely stored in these transient structures, they would be constantly overwritten and degraded. This discrepancy between the dynamic nature of synapses and the persistence of memories suggests that the synaptic theory alone cannot fully account for the complexity of human memory. Section 1. The temporal paradox, synaptic instability and memory persistence. The synaptic theory, while providing a useful framework for understanding certain aspects of memory, stumbles when confronted with the remarkable longevity of human memories. Our ability to recall events from decades ago, even with vivid sensory details, seems at odds with the transient nature of synaptic connections. If memories were etched into the very structure of synapses, one would expect them to fade and degrade as these connections are constantly remodeled and renewed. The proteins that form the building blocks of synapses have a limited lifespan, turning over at a rate far too rapid to accommodate the persistence of lifelong memories. Imagine a vast library where the books are constantly being shuffled, rewritten, and even discarded. Could such a dynamic and ever-changing system reliably store information for decades on end? This analogy highlights the inherent challenge of reconciling the ephemeral nature of synaptic connections with the enduring nature of human memory. The temporal paradox, as it has been termed, exposes a fundamental limitation of the synaptic theory. It suggests that the search for the engram, the physical trace of memory, may need to extend beyond the confines of individual synapses. Section 2. The problem of precision, neural noise, and memory accuracy. Another challenge to the synaptic theory arises from the inherent noise within the nervous system. Neural communication is not a perfectly clean and precise process. Signals are constantly bombarded with random fluctuations and interference, a phenomenon known as neural noise. This inherent randomness poses a problem for any theory that attempts to explain memory as a precise pattern of synaptic connections. If memories were encoded in the specific strengths of trillions of synapses, the constant background noise of the nervous system would inevitably corrupt and degrade these delicate patterns over time. Imagine trying to transmit a complex message using a series of flickering lights, each prone to random bursts of brightness and dimming. The message would quickly become distorted and unreliable. Similarly, the intricate patterns of synaptic connections that supposedly encode our memories would be highly susceptible to degradation in the face of constant neural noise. The remarkable accuracy and fidelity of many human memories, even after decades, seem at odds with the inherent imprecision of neural communication. This discrepancy raises further doubts about the adequacy of the synaptic theory as a complete explanation for memory storage. Section 3. Beyond the synapse. The search for the engram continues. The challenges posed by synaptic instability, neural noise, and the extraordinary capabilities of HSAM individuals have led some scientists to propose alternative models of memory storage. These models explore the possibility that memories might be encoded not just in the connections between neurons, but in other cellular or molecular mechanisms within the brain. One intriguing avenue of research focuses on the role of glia, a type of non-neuronal cell in the brain that outnumbers neurons 10 to 1. Traditionally relegated to a supporting role, glia are now recognized as playing a more active role in information processing and potentially even memory storage. Other researchers are investigating the potential role of epigenetic modifications, changes in gene expression that do not alter the underlying DNA sequence in memory formation. Epigenetic mechanisms are known to be involved in long-term cellular changes, making them attractive candidates for explaining the persistence of memories over time. While the search for the engram, the elusive physical trace of memory, continues, it is becoming increasingly clear that the answer may lie beyond the confines of the traditional synaptic theory. The complexities of human memory demand a more nuanced and comprehensive understanding of the brain, one that embraces the dynamic interplay between neurons, glia, genes, and the environment. Section 1. Experts speak out. A chorus of dissent against brain-centric memory. The quest to pinpoint the precise location and mechanism of memory storage in the brain has been a long and arduous one, marked by both tantalizing clues and frustrating dead ends. While the synaptic theory has held sway for decades, a growing chorus of neuroscientists and psychologists are expressing skepticism about its ability to fully account for the complexities of human memory. These dissenting voices, far from being marginalized, are gaining traction within the scientific community as they highlight fundamental limitations of the brain-centric view of memory. Their insights, often drawn from years of meticulous research and clinical observation, challenge us to reconsider long-held assumptions and explore alternative explanations for this enigmatic phenomenon. One of the most vocal critics of the synaptic theory is Dr. Robert Epstein, a senior research psychologist who argues that the brain, rather than being a storage device for memories, functions more like a receiver and transmitter of information. Epstein contends that memories are not physically stored in the brain at all, but rather accessed from a field of information that permeates the universe, a concept reminiscent of the ancient Greek notion of the Akashic records. Equally compelling are the arguments put forth by neuroscientists like Dr. C.R. Gallistel and Dr. Adam Philip King, authors of the groundbreaking book Memory and the Computational Brain: Why Cognitive Science Will Transform Neuroscience. Gallistel and King point to the lack of a plausible mechanism for encoding and retrieving complex information using synaptic connections alone. They argue that the brain, while undoubtedly involved in memory processes, may not possess the necessary hardware or software to function as a true storage device for the vast repertoire of human experiences. Section 2. The encoding problem. Can synapses really store complex information? The sheer complexity of human memories, encompassing not just factual information, but also sensory experiences, emotions, and even abstract concepts, raises significant doubts about the ability of synapses to serve as the sole repository of such rich and multifaceted data. Can the simple strengthening or weakening of connections between neurons truly account for the vividness and detail with which we recall past events, or the nuanced emotions that accompany these recollections? Consider the memory of a childhood birthday party. It's not just the factual details, the date, the location, the names of the attendees that come to mind, but also the sensory tapestry of the event. The smell of freshly baked cake, the sound of children's laughter, the feeling of excitement and anticipation. To encode such a multi-layered experience solely in terms of synaptic strengths seems akin to trying to capture the entirety of a symphony using only a series of ones and zeros. Moreover, many memories are not simply static snapshots of the past, but rather dynamic and evolving narratives that are constantly being updated and reinterpreted in light of new experiences and perspectives. The synaptic theory struggles to accommodate this dynamic nature of memory, as it implies a fixed and immutable representation of past events. The encoding problem, as it relates to memory storage, highlights a fundamental mismatch between the richness and complexity of human experience and the relatively limited information-carrying capacity of individual synapses. While synaptic plasticity undoubtedly plays a role in learning and memory formation, it seems increasingly unlikely that it can fully account for the vast and intricate tapestry of human recollection. Section 3. Beyond the hardware-software analogy, rethinking memory metaphors. The prevailing view of the brain as a biological computer with memories stored as bits of information in neural circuits, has dominated neuroscience for decades. While this analogy has proven useful in some respects, it may ultimately be too simplistic to encompass the true nature of memory. Just as the heart is more than just a pump, and the lungs are more than just bellows, the brain may be engaged in processes that transcend our current understanding of information processing and storage. To unravel the mysteries of memory, we may need to move beyond the limitations of the hardware-software metaphor and embrace new ways of thinking about how the brain interacts with the mind and the world around it. One alternative metaphor that has gained traction in recent years is that of the brain as a receiver and transmitter of information, rather than a storage device. This view, championed by researchers like Dr. Rupert Sheldrake and Dr. Dean Radin, proposes that memories are not physically stored in the brain, but rather accessed from a field of information that permeates the universe. While this concept may seem radical, it finds resonance in ancient spiritual traditions and even in some interpretations of quantum mechanics, which suggests that information can exist in a non-local and entangled state. Whether or not this proves to be the ultimate explanation for memory, it highlights the need for open-mindedness and a willingness to consider alternative perspectives in our quest to understand this fundamental aspect of human experience. Section 1. The limitations of the computer analogy. Brains are not hard drives. The comparison of the human brain to a computer has been a popular analogy for decades. It's easy to see why both systems process information, make decisions, and store data. However, as we delve deeper into the complexities of memory, the limitations of this analogy become increasingly apparent. The brain, unlike a computer with its neatly organized files and folders, does not store memories in discrete, localized regions. Instead, memories are distributed throughout the brain, with different aspects of an experience encoded in various neural networks. Retrieving a memory is not like accessing a specific file on a hard drive. It's more akin to reconstructing a fragmented image, with different pieces of information pulled from various areas of the brain and woven together into a coherent whole. Furthermore, memories are not static entities like digital files. They are dynamic and malleable, subject to change and reinterpretation over time. Each time we recall a memory, we are not simply accessing a pristine original, but rather creating a new version, influenced by our current emotional state, beliefs, and experiences. The computer analogy, while helpful for understanding certain aspects of brain function, ultimately falls short of capturing the dynamic and fluid nature of human memory. Section 2. The brain as orchestra conductor, a symphony of information. If the brain is not a computer, then what is it? Perhaps a more fitting analogy is that of an orchestra conductor. Just as a conductor doesn't contain the music itself, but rather guides and shapes the performance of the orchestra, the brain doesn't store memories in their entirety, but rather orchestrates the retrieval and integration of information from various sources. Imagine the brain as the conductor, standing on the podium before a vast orchestra of neurons, each representing a different aspect of experience. When we recall a memory, the conductor raises their baton, cueing the different sections of the orchestra to play their parts. The strings might evoke the visual imagery of the event, the horns, the emotional resonance, the percussion, the rhythmic patterns of sound. The conductor doesn't dictate every note played, but rather provides a framework and direction for the overall performance. Similarly, the brain doesn't store memories as exact replicas of the past, but rather provides the cues and connections that allow us to reconstruct experiences from the fragments of information distributed throughout our neural networks. This analogy emphasizes the dynamic and emergent nature of memory, where the whole is greater than the sum of its parts. It also highlights the crucial role of the brain as a coordinator and integrator of information, rather than simply a storage device. Section 3. Beyond the material, exploring the mind-body connection. The limitations of the computer analogy and the emergence of alternative metaphors like the orchestra conductor point to a growing recognition within neuroscience that the brain, while undoubtedly essential for memory, may not be the whole story. Could there be factors beyond the physical structure and function of the brain that contribute to our ability to remember? This question delves into the age-old philosophical debate about the relationship between the mind and the body. While materialism, the dominant paradigm in Western science, reduces all mental phenomena to physical processes in the brain, other perspectives, such as idealism and dualism, propose a more complex interplay between the mind and the body. Idealism, for example, suggests that the mind is the fundamental reality and that the physical world, including the brain, is a manifestation of consciousness. Dualism, on the other hand, posits that the mind and the body are distinct entities, interacting with each other but not reducible to one another. While these alternative perspectives are often dismissed as unscientific or even mystical, they offer intriguing possibilities for understanding the nature of memory. If the mind is not simply a product of the brain, but rather a separate entity or even the fundamental reality, then the brain's role in memory might be more akin to a receiver and transmitter of information, rather than a storage device. Section 1. Beyond the brain. Embracing a new understanding of memory. The evidence presented throughout this exploration of memory paints a compelling picture. The brain, while an essential component of memory processes, may not be the sole or even primary storage site for our experiences. The limitations of the synaptic theory, the extraordinary capabilities of HSAM individuals, and the insights of numerous neuroscientists and psychologists all point towards a more nuanced and expansive understanding of how memory operates. We've seen that the fleeting nature of synaptic connections, the constant hum of neural noise, and the sheer complexity of human experience pose significant challenges to the notion of memories as neatly encoded patterns etched into the brain's physical structure. The brain, rather than a static repository of data, appears to function more like a dynamic and ever-changing orchestra, weaving together fragments of information from various sources to create the tapestry of our recollections. This shift in perspective, while challenging long-held assumptions, opens up exciting new avenues for understanding the true nature of memory. It invites us to consider the possibility that factors beyond the material realm, such as consciousness, energy fields, or even quantum entanglement, may play a role in how we store and retrieve information. Embracing this expanded view of memory requires a willingness to move beyond the limitations of the traditional hardware-software analogy and acknowledge the profound interconnectedness of mind and body, brain, and universe. It calls for a more holistic approach to scientific inquiry, one that recognizes the limitations of reductionism and embraces the complexity and mystery that lie at the heart of human experience. Section 2. The future of memory research, expanding the horizons of inquiry. The realization that memory may extend beyond the confines of the brain has the potential to revolutionize not just neuroscience, but also fields such as psychology, medicine, and education. As we delve deeper into the mysteries of consciousness and the mind-body connection, we can expect to uncover new insights into how to enhance memory, treat memory disorders, and unlock the full potential of the human mind. Future research in this area will likely explore the role of non-neuronal cells, such as glia, in memory processes. These often overlooked cells, once thought to play merely a supporting role, are now recognized as crucial players in information processing, and may even hold the key to understanding long-term memory storage. Further investigation into the role of epigenetic modifications, changes in gene expression that influence how our DNA is read and expressed, could shed light on the molecular mechanisms underlying memory formation and persistence. These epigenetic changes, influenced by both our genes and our environment, may provide the missing link between our experiences and the enduring physical traces of memory. Exploring the intersection of quantum physics and neuroscience could yield groundbreaking discoveries about the nature of consciousness and its role in memory. Concepts such as quantum entanglement, where particles are linked across vast distances, might offer a framework for understanding how memories could be stored and accessed non-locally, beyond the physical confines of the brain. The journey into the depths of human memory is far from over. By embracing a spirit of open-mindedness, collaboration, and a willingness to challenge dogma, we can look forward to a future where the mysteries of memory are gradually illuminated, leading to a more complete and awe-inspiring understanding of what it means to be human.